Hello and welcome to my presentation on lessons learned from two DDoS attacks on resolver host. My name is Dejan Donin. And let me start with saying that I'm sorry that I'm not able to attend this conference in person. I'm really looking forward to do it, but a family emergency came up and that kind of prevented me to arranging the travel at this time. I'll be glad to answer any questions after the talk in the chat. Let me say a couple of words of how this talk came up. So, essentially, this talk was conceived during a hike in Squamish in close to Vancouver with Brian Somers. And we were kind of informal talking about some operational issues that happened on the OpenDNS fleet. And we kind of thought that maybe this is an interesting topic to share with the broader audience and share some of the lessons learned from these two attacks that we discussed. Hmm. All right, so let me start with the kind of introduction on these DDoS attacks. So the DDoS, the large-scale distributed denial of service attacks, are relatively common. And Cisco's fleet is no exception in kind of experiencing these. And these attacks are normally not even noticed, but because they are kind of mitigated by distributing traffic over resolver capacity, installation size. So then it's kind of those queries are lost in the noise of many other queries. That's one way of doing it. Kind of uh, limiting the scope of the attack. The other way is the various kinds of rate limiting of the queries. So the clients, the same clients bombard the network, it will start being rate limited. Even if there is a small pool of those clients, the rate limiting will limit their influence on the operation. So that all leads to these issues, operational issues are rare, but we did have some incidents that uh, were noticed and remediated. Um, so thankfully, in both cases, we want to share the customer impact was relatively limited, and the cases were relatively quickly uh, solved. Um, and we will now share how we did that and how was detected, how was remediated. So in both cases, the incidents were detected by alarms. So we have various kinds of alarms connected to the resolvers. They detect different operational parameters if they go out of the expected range. The alarm will kind of inform the person on call what's going on. Uh, Most common DDoS attacks are the alarms that indicate the delayed traffic servicing, the slower servicing of the queries, or delayed configuration updates. The configuration are regularly pushed to the resolver fleet, and if they're not applied on time, we would notice it and send an alarm. And that happened in these cases. So uh, on the surface, these attacks look similar. There were delayed processing, but the underlying case issues were different. In the first incident, which is we will call them DNS traffic surge, um, we've seen something like this. So there is transaction round trip times per second. The green is good. The rainbows are a sign of trouble, which means the queries are processed slower. So all these bins of processing times, the bins for larger processing times are incremented and kind of dominating here in this period of time. So as you can understand, we can't share the details of where and when exactly this happens, but I'll share other details, technical details that can be publicly uh, shared. So This DNS script traffic surge attack was a random label attack, and then started pretty much at one data center. So the random label attacks usually end up causing a host name that's not found in the cache. The host, the name is sent to authoritative name server to be resolved, and that at some time, if our resolvers do not rate limit it enough, then there's too many of these requests sent to the authoritative name server, and then authoritative name server itself starts doing the rate limiting of these requests from the DC. So we've seen that as well. So in this case, we tried to at the beginning we tried to remediate this by blocking the attacking IPs. This is not a very popular choice, or we really it's kind of a last resort case if it's unknown why something is going on, and we think that there are too much traffic from attacking IPs that are not limited for some reason, but the pool was pretty large of these IPs. So it was a relatively sophisticated attack, and it was not easy to block them. So the attacker was employing a very large infrastructure of hosts, or maybe it was spoofing the IPs for this attack. So then we had to dig deeper. What was noticed is that there was an increase in the DNS traffic during this incident. So DNS script is used to kind of encrypt the DNS traffic. It can be used by the client. In this case, this was also used for the inter resolver or inter DC communication. Um, Client-based DNS script traffic is very, very low. Amount of the volume of this traffic is relatively low. But then in this case, we suddenly saw a really high spike in this traffic. So, and this really amounted to coincided with the amount of traffic that was rerouted from one DC to another one, which really happens when the authority doesn't respond. And that's common in DDoS attacks. And what happened is really that one data center referred queries to another data center authorities, and to ask another data center or another resolver in another data center to see, okay, do you have this domain name in the cache? Can you help me out? That traffic itself, that referral of the query from one resolver to another in our implementation is implemented using the DNS script. That's done for safety and security. And that traffic was jumping in this case of this DDoS attack. Once we've seen this kind of led us to unravel the problem. So in the weeks ahead before this incident, we deployed the change in the DNS script protocol itself, and that was an upgrade of the DNS protocol to make it compliant with the FedRAMP requirements, and basically improve the encryption used there. But that change also inadvertently set caching lock contention configuration for DNS script transmission, and that meant that this key pair for the DNS script was continuously being calculated again, regenerated, and serialized for this transmission between data centers. And that itself, which is a very computationally expensive operation, that itself created bottlenecks, underload, because there were a lot of queries being referred to, and kind of downstream caused the backlog for processing of the queries itself. Essentially, the fix was change the lock contention configuration, software update. Once the software update was deployed, the fleet handled this attack well. Okay, next one incident, maybe even more interesting, was the short-lived DDoS attack. This was a very short-lived one and difficult to analyze. Um, it had the signature of the attack was in bursts, also the random label attack. It was lasting a couple of minutes and stops, as if somebody was probing the infrastructure. It happened in a different data center at a different time, so I don't think it was related to the first one. And it was short, but caused, again, alarms, and then it just goes away. So it was very hard to track. And it would happen a couple of times, again and again, over a week's time, I believe. We were not, it was very easy to see what's going on. It was not very easy to see what's going on. So the only once we were able to kind of capture the state of the processor that was the processor in during one of those incidents, we noticed that the processor thread states revealed that threads were spinning in a lock. So, and this lock itself that we noticed that kind of was blocked, well, it was controlling an access to the list of in-transit upstream queries. So the upstream queries, again, the queries that are going to the authority, which are usually elevated in these DDoS attacks, are chained. So the chain means like they're bundled and sent in bundles to the authority. And to decide which bundle to use, we have these groups or the locks that control which bundle to use. And then really how to do that, we would query domain's name, we would hash it, fold it into 12 bits, and determine which or96 locks would be used. So there's a lot of locks that's used for reducing the contention, and that will reduce the contention, but only when good hash distribution is used. And that turned out to be the Achilles heel of this um, this algorithm, or the way how we were doing the hashing. So the hashing was basically using the first queue name label, the target IP address. And the reasoning was, okay, these are the most volatile transmission data parts of the whole whole host name. And but in this case, that was not the case. The random label attacker in this case was of the form a constant .random domain, and that always ended up being hashed to the same value and the same lock, as shown in this figure below. For example, we are caching all this www using the same hash function, we all get the same hash value. We will try to be prudent and save on computation by hashing the least amount of data to to make the algorithm faster, but that also caused an issue here. So basically, all the random label domains were hashed to the same value, again leading to serialization and kind of serialization of these queries to the upstream and backlog. As in the previous case, this was resolved by software updates, changing how this hashing was done, and this was a relatively simple fix. And after that, we did not notice these problems again. Well, kind of in conclusion and the resolution details. So these were incidents that are affected different resolver resources, and on the surface looked same, but they were caused by different operational issues and software implementation issues. It's interesting that these lock contention issues in both cases escape detection despite extensive tests. We have unit, application, and performance tests. The most interesting is that it escaped the performance test. And there is actually a reason behind that. So the performance test was using a known kind of corpus of domains for these tests. So like some 1 million I think, and or some variant of it, and basically it was not designed to test itself the DDoS type of attacks. And this performance and application tests are used in kind of release pipeline. So and these tests did not notice this kind of issues ahead, and only the kind of operationally we were noticed it and fixed it relatively quickly, as I said. And that kind of emphasizes the need for these types of tests as well in the software release pipeline. And that concludes my talk. Thank you for your patience, and I'll be glad to answer your questions and comments in the Mattermost channel. Thank you.